These devices which have a lot of calls on simultaneous there's a new one just been announced which has 100 calls. It's another device.
Kropka na pewno jest mocnym
They
mocem.
have also separate memory.
No to jest moc.
I think I heard that each
Nie da się
core has its
trochę
own
więcej
memory.
nieruchomości. Gdzie to urządzenie ma głośnik? O, wiesz co tutaj jest? To z góry, bo strasznie cicha kropka wychodzi i na nim wychodzi cicha kropka. No nie ma teraz jakiegoś wielkiego hałasu, on nie daje rady wzmocnić sensownie dźwięku. To się zdarza, czy to się nie powiem? Czy to jest po prostu cicha próbka? Ja nie są jakieś kolejne próbki? No wiesz, czy coś powinno być widać? No tak. Znaczy projektor się wyłączył.
Whereas if you're trying to get a series of
tego też prawie w ogóle nie słychać.
Also, there are two different interesting things. First is we don't try to make to synchronize stuff. We just try to let it replicate that enough times not to fail. Yes, that's the way. Let's say big databases work like Cassandra. They don't try to synchronize with everything. They just try to synchronize enough.
Let it go ahead. So there's some techniques there.
Dobra, to włączmy może tam prezentację w ogóle.
State update. One is basically saying, okay,
To jest coś takiego. Opuszczono w jakiś sposób dwa ekrany. To było dobrze. To sprawdzić, czy ta muzyka idzie. Myślisz, to trzeba kliknąć. Albo tak, albo z tym mikrofonem jest troszeczkę lepiej, natomiast... Co mogę z mikrofonem? No, to trzeba połączyć pana. W sensie...
So if we've got things threats, then the amount of overhead per thread needs to be reduced. What I'm actually doing with the example I showed you is I was running this on about 8 cores. What I was doing was to minimize the total number of threads to some smaller number. Basically, by absorbing work, automatically absorbing work. If what you have is fully functional, then when you create a future, you don't actually have to Yes, but you still need to have enough. So you need to have enough work that if you have a future assembly, you'll have the work available. But you will, if you don't have a lazy future assembly, which is basically functional, then you will have to execute work that each of those threads will carry over.
Chyba, że próbujemy to zakres z innego komputera, żeby mieć mocniejsze
Tak, ale nie ważne, bo to nic tego nie ma. Raz, dwa, trzy, cztery.
Do końca trzeba go przełączyć. Teraz.
Raz, dwa. Słychać?
Z tego coraz lepiej.
Weź tam gdzieś. No. Raz, dwa. Słychać? Raz, dwa. Jest ok? Może tutaj trzeba to zgłosić. Aha.
To wszystko idzie po prostu przez pytanie, gdzie najłatwiej.
Raz, dwa. Jak? Lepiej? Okej. A teraz? Tamten?
generalnie cicho mówisz i to faktycznie, że trochę nie...
Alright, ladies and gentlemen, we are about to begin. I should say it very, very loud so that I'm audible outside. Kamera obejmuje tak mniej więcej od końca tego plakatu i tutaj i
Całą prezentację.
także za to raczej nie wychodzi.
Dobra.
The next talk will be given by Jakub Korczyński, and it will be about the Forte framework for music composition. Please welcome our speaker.
Okay, thank you very much. I'm very pleased to give this talk for you today because I'll be speaking not only about functional programming, about Haskell, embedded DSLs, but also about music, one of my passions. And I hope thanks to this talk, you'll understand more about music and maybe you'll also become fascinated by it like me. So I would like to start with this quote from Igor Stravinsky, who was a renowned composer from the 20th century, famous, for example, for his ballet Rite of Spring. And he had this statement that art is the contrary of chaos. And what this means, what I think this means, my interpretation of this quote is that especially nowadays in modern art, in modern music, where everything is allowed, you can do just about anything. It's not like in medieval times that you have had the church impose certain rules on what you can do, what you cannot do, what notes you can use, what sounds you can use. Now you can do anything. Anything is possible. And in this world, where anything is possible, how can you communicate with your listener? If you can just put some random notes that are really incoherent, and how can you communicate with your audience if they can't understand your language? So I think this is what Stravinsky meant when he said this, that it is very important that you impose certain rules, certain frameworks, and systematics on art that you are performing. It can be music, it can be painting, it can be anything. Okay, so the first thing I would like to start with is the definition of the problem. Here we have our national pride, Chopin, playing the piano. He was a virtuoso piano player, and in my opinion, the problem, well, not only in my opinion, but many people throughout the ages have tried to grasp music and try to analyze it, try to understand it more fully than just at the level of emotion. We have a little sound problems, but this is the A minor etude by Chopin. And I'll try to show you how we can map this piece of music that is really just a sound wave to numbers so that we can further analyze it through mathematics. And like I said before, people are trying to do this for ages, try to better understand musical styles and art itself, not only in music. And when it comes to my favorite domain, there's a partial solution for this, and that's notation. That piece that we heard a moment ago, that for some less musically inclined, maybe very even abstract, can be noted like this in classical romantic notation. But in my opinion, this is only a partial solution because at first glance, we don't see the patterns. If somebody is trained in musical analysis, then he can, just by looking at just a short glimpse, he can already have some conclusions about this piece. But for most of us, it's not that obvious. What we can do is we can take the notation we saw earlier and map it onto numbers, like this. And I'll explain how we do that later on. But we can do even better, because we can take it to the next step, next level, further normalize these patterns, and we start to see various patterns emerging here. And I'll also tell you how we can do this. And going even further, we come to this, and it turns out that that piece of music that may sound to some of you very complicated, very virtuoso piano playing, is just simply the chromatic scale and some minor, major chords in the harmony. So what this really is about is taking the sound wave, taking art, transforming it to some known notation, and then further on through numbers and applying mathematics, we can see that in essence this can be reduced to this up there. And now, to somehow aid composers and musical analysts in their quest for learning about music, for composing, I propose a framework, a set of tools, 2 languages that enable you to do this process efficiently. It's called the Forte framework. The whole framework consists of 2 embedded domain-specific languages. The first of which, its task is to manipulate on the pitches we saw earlier in the notation. We can take those pitches, and the whole point of the DSL is to transform those pitches into numbers. So we can have this mapping, and we can later on process those numbers, thinking in mathematical terms and not in abstract musical notation. And that's the whole point of the first of these languages. And the name comes from the surname of Alan Forte. He was a musicologist that took together the writings of Babbitt and Pearl and proposed what became later known as Forte's theory of musical analysis. And like I said earlier, all we do here is map musical notes to numbers. And how is this done? If we could take into account, let's say, the classical music notation, everything we have in pop music, rock music, jazz music, all the popular music, classical music, most of the things we hear, I'm not talking about very experimental modern music right now, we have just 12 pitches. Because we have something like octave equivalence, meaning that every time a wave doubles in frequency, we hear it as almost the same pitch. That's why we can basically reduce our analysis to only 12 pitches. So what we can do with those 12 pitches, we can just label them as numbers. And when we have those numbers, that's when mathematics comes in, and we can further analyze those numbers based on mathematical dependencies between them. So in essence, Forte's theory maps those pitches of any musical piece to what he called pitch classes. He does the same with intervals. Intervals are the relationships between individual pitches. And later, he groups those pitch classes into what he calls pitch class sets. Pitch class sets, like the name suggests, are just sets of pitch classes, and it occurs, there's of course a finite number of them, and what Forte did, he proposed a classification of all those pitch class sets. So in the end, we have a nice structurized, mathematically based classification of various musical structures and possible interval combinations, which is I think it's a very cool thing, because when we try to later analyze a piece, we can really find out what its intervallic content is and its essence and how it should sound. So the process, what it basically does, if we take a piece of music like this, Claude Debussy, I think this piece was also the first part of Twilight, if anybody watched that. This is just another example. We take this piece, and we see that in essence it's only these two pitch classes. So again, this is a pitch class. We have individual pitches starting from C. These are their labels, and we have them grouped in a set. So you see that in a piece like this, we have two structures, one that has 3 pitch classes, one that has 4, and we see the structure and the relationships between the notes thanks to this mapping. Summing up, when it comes to Forte's DSL, the Forte DSL part, what I've done is I systemized the theory. There were some minor mathematical, let's say, inconsistencies in the whole theory, and I proposed some techniques for the abstraction of the domain, but I won't go into detail now, because I would have to take more time into explaining the whole concept, how the domain could be abstracted at various levels to, like it's stated here, avoid much boilerplate and allow for interpretation swapping. So I'd like to now cover the second of the languages. It's a language focused on graphs, and both of these languages in the framework are really independent of each other, and I'll later tell you why. But when they come together, you can use them for musical analysis and composition. We have the graph DSL, which is going to be a language for graph manipulation, but it will also allow us to grasp the construction of a musical piece. And I'll now show you 3 fundamental concepts of any musical piece and how we can map those concepts onto a graph. Okay, so the first thing we want to do, like I said, is modeling music as a graph. And we have 3 things we have to deal with. First is time, and a graph is good for, in my opinion, for modeling music, because we can, if we have a directed, we have a DAG, a directed acyclic graph, we can treat the depth of the graph as another point in time. So I'm going deeper into the graph. We progress in time. And that's the first thing. The second thing is the vertical planes. So if somebody, a musician is talking about harmony, and for example, what he hears is some chord in a given point of time, that would be the vertical plane. So if we go through the, take the whole one level of the graph and check all those structures, all those nodes on that level, and we arrive with the harmony at a given point of time. And the third thing is our horizontal planes and musical paths. By this, I mean, for example, if you take classical music, it's the harmony is there's, like you could say, one harmonic plane. It's quite simple. In more advanced modern music, you have many harmonic planes. They can be independent of each other. You can, for example, have some minor major harmony at the top, some modal harmony at the bottom, some jazz harmonics in the bass. And you have to have a way of modeling that. And in a moment I'll show you on real notation how this looks. So to give you an example, when using this graph DSL, finally we get this graph. That's a picture of our musical piece. And in the nodes, what we have here are pitch class sets. So this is from Forte theory. But like I said, languages are independent. I could, for example, have here just some tabular notation or some other Western, Eastern music notation or anything else. But together, you can use them for Forte analysis. Okay, so once again, the first concept, to show you an example. So the musical time window. If we have a graph like this, we can interpret it in time in various ways. This is a proposal, because this is the Chopin piece we heard at the beginning of the talk. And, for example, we can treat 4 levels of our graph as a whole bar of music. And so we get each level as a quarter note. But, of course, in modern music, we have the notation not of quarter notes and whole notes, but we have, for example, we can put specific time frames like 3 seconds. That some music has to last 10 seconds, 5 seconds. So we can treat this as any time interval we really wish to. So this is this graph model, in a way, abstracts from concrete time. We can later, as composers, set the time as we wish to. So mapping it onto this piece by Chopin, the Etude in A minor, we have those quarter notes and those bars, and it's quite an obvious mapping. But what's also important, why do we have to have these levels? These are our, like I said earlier, vertical planes. So if we take this, you can think of this as the music we hear in a point of time, because music is a very specific art where time passes and it all happens in relation to time. So this is very important in analysis, that we can stop frame and see what's really going on at a given moment of time. And this is the same, like in notation, we have that quarter note. And also the horizontal plane I mentioned earlier. We can divide our analysis into, for example, 2 parts. Like in case of Chopin, we have the melody and the harmony. Very, very classical setting. And we could see it on the notation. So harmonic and melodic at the top. Okay. I won't have much time to go into details of the code, but I want to show you a real example. Okay. So just to get a feel of how the DSL finally looks like. If you want me to tell you more about it later, you can catch me in the corridors, and I'll gladly explain. This is how it looks like, but in a few words. What we're doing here is we're applying transformations on our structures. This, for example, is transposition. Very simple and fundamental musical operation where we take a piece of music and transpose it. So we add frequency, but we take the whole structure and add frequency to all the components at the same time. And when we have something like this, which happens to be this, we can map those time values I talked about to receive this, and we can find a very good piano player who can receive sound. So in the end, we have our Chopin piece. Okay, so thank you. If you have any questions, feel free to ask me after talk.
Thank you very much. We still have some time for the questions. Are there any? Please.
Short question. Hello. Do you have some kind of paper or thesis about this?
Yes.
Where is it?
Well, there's supposed to be an article in the journal here, but I'm still working on it. But I have a thesis. Yes, it's quite long. A lot of. If you leave me an email, I can send it to you.
Some more questions?
Did you bother using wavelets for your problems, or that's DSL for representing music using I don't know, some kind of notation?
Okay, so my focus was more on the higher level, not operating on signal, if that's what you mean. I rather focused on, in this project, on pitches, but you can also easily extend this project to, for example, rhythmic values and so on. But it's not about low-level sound synthesis, but rather on, like, I would say a typical composer's approach, more on the higher level.
Okay, and one final question from the very end of the room.
Well, just a couple of questions and comments about your framework. Well, as far as I understand, the purpose for which the framework was developed, you developed that framework because you want to provide another way to understand the music. Well,
yes.
all right. Yep.
Understand, but also to reverse the process and be able to compose music, thinking the other way around, not just that we find some piece of music and look at its structure and find dependencies.
Okay, I have it.
Yeah.
Actually, a couple of years ago, maybe 10 years ago, even more, I deal a little bit with music and musicologists, and the first observation is that when you, for instance, want to differentiate between, let's say, Japan music or Chinese music and folk European music, the most important things are just some small pieces of music, not the music as the whole, but some different and specific for different types of music intervals. So, if you want to, for instance, use your framework for automatic recognizing music, you probably need to focus on very specific parts of melody or music, not on the classes or phrases of melody or music. This is just one comment. Another comment is I'm not sure whether you are aware of another languages that was made or developed for the purpose of music analysis or music understanding. One of them is ASAC software, ASAC language. ASAC is an abbreviation, as far as I remember, of Essener Associative Code. It was developed by Ulrich Franzke, who's a German researcher. And, this language, ASAC language, is used for musicologists to write down folk music from different parts of the world, in Europe in particular, and analyze and find the differences between different types of folk musics. So if you are interested in that kind of software or databases, let me know. I can give you a context for people who deal with that stuff.
Okay.
That's it.
Okay, do you have any other questions? Sure.
So you can represent quite complex music with some simple data. I'm wondering if you tried to feed your algorithm with some random data and then sell the music it creates.
Okay. I didn't do this in this project. I, for example, tried to generate music out of fractals. Just take fractals and map them in some way to pitches and rhythm. And sometimes the pieces sound like they're cool. It depends on a little bit of luck, of course, and the mapping you provide. But in this project, I want to focus less on algorithmic generation of music. It's more for really for composers, so that before they start, for example, writing a symphony or something, they can first lay out the whole structure in the form of the graph I showed you. So at least the basic harmony is visible to them, because the problem of modern music is that you don't have the safety of the major-minor system or any other system at your disposal. It's rather that the composer has to think of some of his own stuff. He has to have his individual system, composing method, harmony, and so on. So if it's an aid to those composers, because they can easily plan the whole piece using this graph structure. They can think of some harmony, some structures they like, and they can construct the piece from scratch without the aid of any fixed system that already exists. They can create their own systems with ease.
All right, thank you very much. Let's thank our speaker once more.
Thank you.
And right now we're going to have a break. We'll just change it. 3 minutes break? Okay. All right, so we'll have just a technical break, 1 or 2, 3 minutes, as much as it takes to connect different computer, and we'll start another talk immediately.
Muszę zobaczyć, czy to będzie działać.
Niestety musimy odebrać.
Okej. Myślałem, że mogę sobie znowu pobrać.
Spory zasięg nie zabierze, ale to streaming cały czas leci?
No, świeci się, więc chyba tak.
Internet? Bardzo dobrze.
A nie może być ten?
Może być, ale ten też, bo ten jest nagrywany przez Cisco. Czy gdziekolwiek, tak żeby tylko sobie ten dał?
Czemu nie puszcza się nic? Nie podane sygnał?
Tylko jeszcze zobaczmy, czy to jest to.
Dobrze, by było to samo.
Tutaj.
Tego to nie wciskaj, nie?
Czego?
Coś tu.
Nie. To jest. To jest tutaj. Znak sygnału na jedynce, a to był wtedy chyba na jedynce.
Tak, na pewno. Coś tutaj.
Czekaj, co się dzieje? Jest.
Jeszcze ją sobie sklonował.
so let's start the final talk of this part of the research track. Mr. Rafał Studnicki will tell us if is it possible to run Erlang on 32 kilobytes of RAM. Please welcome our speaker.
Hello? Can you hear me? Can you hear me? Here? Okay. So before we start, I have a very important warning for you, because this presentation contains the Internet of Things buzzword. So if you think that you're allergic to it, you're attending at your own risk. So formalities continued. In this very short presentation, I'm going to ask the question that you have already seen on the first slide. So is it actually possible to run Erlang virtual machine using just 32 kilobytes of RAM? I'm going to explain why I asked this question about 18 months ago, and I will obviously try to answer it somehow. So besides being a speaker right now here, who actually am I? I have recently graduated from this university, although not this particular faculty. For some time now, I also have been working as an Erlang developer at Erlang Solutions, spending most of my time developing stuff related to the Mongoose IAM XMPP server. And also, as you could have read on the Lambda Days website, I call myself a wannabe embedded hacker. And by this I mean that, well, I have actually no theoretical knowledge. I just like to play with cables and stuff. So that's the infamous IoT slide. So the current research shows that right now there are almost 7 billion connected devices around the world. And this number will be even bigger by 2020, and it will reach about 50 billion. So if you think that I made up these numbers, well, I also attached some source. You think that I made up the source as well? Well, there's one thing that we cannot deny, and that's something that I call something like embedded bubble, which started like about 2.5 years ago when the first version of Raspberry Pi was released, and every high-level language programmer started to build its own embedded stuff on top of Raspberry Pi and similar boards. So I was not an exception, and because of this, I call myself a wannabe embedded hacker. At the same time, actually, I was thinking of my Master of Science project topic. So, I thought, what if I actually can write some embedded stuff using Erlang? Well, obviously, it would have some pros and cons. Pros like I can very easily prototype stuff, and I don't need to worry about memory management, concurrency, and so on. Obviously, it would be very slow because of the overhead of garbage collection and So obviously, since this is a research track, I had to do some research. What has been done before in this field? Obviously, the Beam virtual machine that you run when you type Erl in the command line was somehow developed for embedded stuff, for ATM switches originally, but it uses almost 30 megabytes of RAM if you start it with OTP loaded, and a little bit less, almost 8 megabytes when you just load the necessary modules. That was too much for me. I wanted to run it on bare metal, so the Raspberry Pi-like boards also were not a choice, since they're using a full-fledged OS like Linux or Unix. Yes, at the same time, there was an effort to build INEA OSE RTOS port for the Beam virtual machine, and I thought that it was really nice. Unfortunately, the OS itself is a proprietary one, although the Beam version for INEA OSE is an open source. So I thought that it's not using the full-fledged OS, it's just a microkernel. So I thought that this is a good way. So I choose another one that is not proprietary. It's an open source microkernel. So I actually have chosen the FreeRTOS microkernel. And I basically decided to write the Erlang VM from scratch. Well, I thought that it's pretty nice. It's using just 230 bytes of RAM when you start it, and the 5 to 10 kilobytes of flash, depending on which modules do you choose, and also provides some useful abstractions, at least in terms of implementing an Erlang VM from scratch, like scheduler or memory management. And at that time, I also owned this little thing, an LPC7069 microcontroller with 32-bit ARM Cortex-M3 CPU on board. And that was the only ARM that I owned, so I chose this one. So it has got 512 kilobytes of flash and 32 kilobytes of RAM. Okay, let me take you on a journey through how my machine was actually developed. So this is every Erlang textbook example of a simple module that I bet most of you can implement it, test it, and compile it and test it in like 2 or 3 minutes, or even less. Simple factorial calculator function that calculates factorial value. However, what I wanted to do was to simply compile an Erlang module on my laptop, like this one, and execute it on an embedded machine. So, well, the code that you have seen on the previous slide is not something that the Erlang VM understands. Well, it's more similar to this. Well, it's a human-readable version of bytecode.